So my name is Neha, and I lead a cryptocurrency group at the MIT Media Lab. And I'd like to talk to you today about some work we're doing on distributed ledgers. Most of the value in the global financial system is in instruments that are transacted through about a dozen large investment banks. These banks trade securities, currencies, commodities, and derivatives. Some of this trading is done through regulated exchanges like NASDAQ, but about 40% is done through these unregulated over-the-counter or OTC markets. This represents trillions of dollars in value, and to give an idea of scale, it's on the order of tens of transactions a minute, so this is not high-frequency trading. These trades are recorded in a database. A useful abstraction for thinking about a table of these trades is a transaction ledger. In a transaction ledger, every row is a transaction transferring assets from one bank to another. So here in the first row, we have Citibank transferring $1 million to Goldman, then JP Morgan transferring 200,000 euros to UBS, and 3 million to Barclays. Sometimes these transaction ledgers use digital signatures to indicate a consent to transfer. In that case, every bank will have a public-private key pair, and the transactions will have attached digital signatures, which show that the spender approves the transaction. This ledger might be maintained by a third party, or it could be maintained in a distributed database run by the transacting banks themselves. There are important financial invariants to maintain in these ledgers, which are the following. First of all, we want to make sure that the spender has actually consented to the transfer. And like I said before, we can use digital signatures to achieve that. But we also want to make sure that the spender actually has the assets that they are transferring, and that assets are conserved. They're neither created nor destroyed in the process of these transactions. In the case of a distributed ledger, everyone can verify and validate transfers by actually looking at the ledger and making sure that these properties are maintained. If the ledger is being maintained by an exchange or a single party, then they can do it. But there's a tension here with privacy, and banks actually care quite a bit about privacy. Trades can reveal very sensitive strategy information. For example, a large trade might indicate that a bank has decided to move out of a position, and if other banks learn about this, then they can follow on and drive down the price. A good technique for achieving privacy is to simply encrypt or hide the transactions in the ledger. This makes verification more challenging, but it's still possible, and other systems have actually achieved this property on distributed ledgers, including two systems, Zerocash and Solidus. But there's still a problem. Regulators need insight into markets in order to maintain financial stability and to protect investors. For example, an auditor or regulator might want to understand how leveraged a bank is, how exposed they are to a certain class of assets. And they might want to understand features of the economic system as a whole, like how concentrated the market is. Lack of insight can have devastating effects, as we saw with toxic assets in 2008. A contributor to the financial crisis was the issue that people didn't have enough insight into exactly how many assets banks had on their balance sheets. So the question is, how can we confidently audit banks to determine risk? For an example, an auditor might want to know how exposed is a bank to a drop in the exchange rate of the euro. They can ask the bank what fraction of your assets are in euros and get an answer back, but the auditor doesn't really have any confidence that the bank is answering correctly or that it's not leaving out certain assets that it might have on its balance sheet. This talk presents zkLedger, which is a private but auditable transaction ledger. zkLedger has the following properties. It provides privacy. It hides the transacting banks and the amounts that they are transacting in. It also provides integrity with public verification. everyone can verify that transactions are well formed, even though they can't actually see them. And importantly, zkLedger provides auditing. An auditor can interactively compute provably correct linear functions over the transactions in the ledger. In the rest of this talk, I'm going to describe the system model for zkLedger, including its security goals and threat model. I'll describe a few key parts of zkLedger's design and how it achieves privacy and auditing, and then I'll show you an evaluation which shows that zkLedger's performance is quite reasonable. So let's start with the system model. So suppose we had a set of banks who were engaging in the type of markets I described before. So they were trading sets of digital assets. These banks, once they've decided on transactions, then append them to a ledger. Now, this ledger is private. Only the parties involved in a transaction can actually see the contents of the transaction. And an auditor can obtain correct answers to queries based on ledger contents. For example, an auditor might ask the bank, what fraction of your assets are in euros? The bank will respond, but the auditor will also have a verifiable proof that the answer actually checks out according to the contents on the ledger. There are a few important things to note here. First of all, auditing is interactive. The auditor cannot compute anything about the ledger without actually querying the bank first to receive the answer. This means that it is possible a bank simply might choose not to respond to the auditor. Frequent auditing will leak transaction contents. For example, if the auditor repeatedly asks this query and the answer changes, it's reasonable to assume that it was the last transaction in which this bank received euros. zkLedger supports any linear function over transaction values. For example, we can do ratios and percentages of holdings, sums, averages, variance, skew, outliers, for example, which transactions have values outside of a certain range, approximations and order of magnitude, so you can reveal the order of magnitude of my assets without revealing the exact number, changes over time, and well-known financial risk measurements like the Herfindahl-Hirschman index. zkLedger does permit a small amount of well-defined leakage. For example, computing the average leaks the total transaction value and the number of transactions for a bank. In this talk, I'm only really going to describe how we do sums, but you can see our paper to see how we achieve all of these other measurements as well. Let's start with zkLedger's security goals. The first goal is privacy. We want to make sure that the auditor and non-involved parties cannot see transaction participants or amounts. Our next goal is completeness. Banks shouldn't be able to lie to the auditor or omit transactions from its answer to a query. Third, we want to provide integrity. Banks shouldn't be able to violate financial invariants, and in particular, an honest bank should always be able to convince the auditor of a correct answer. And then finally, we want to ensure progress. It shouldn't be the case that a malicious bank can block other banks from transacting. zkLedger achieves these goals under the following threat model. Banks might attempt to steal or hide assets, manipulate balances, or lie to the auditor. Banks can arbitrarily collude, and banks or the auditor might try to learn the contents of transactions. What's out of scope are the following. zkLedger assumes that the ledger includes transactions and is available. zkLedger does not protect against an adversary watching network traffic, but both of these two things can be handled using other techniques. And zkLedger does not help if a bank decides it wants to leak its own transactions. Now let's discuss zkLedger's design and how it uses commitments, a novel table format, and zero-knowledge proofs to provide some of these properties. Let's start with an example ledger. So this is a public open transaction ledger, and here we have 4 transactions. We're going to build up zkLedger's design based on this. The first transaction is a deposit. So in zkLedger and in many other ledgers, there are certain parties that are allowed to create new assets on the ledger. For example, a central bank might be allowed to create euros on this ledger. Here, a depositor is issuing 30 million euros to Goldman Sachs. Then, Goldman Sachs is transferring some of these euros to JP Morgan, who then transfers them to Barclays. In our example, we want to provably audit Barclays to figure out how many euros it's holding. And the answer should be 3 million. It's received euros in 2 different transactions totaling 3 million. But we want to achieve this while hiding the participants, the amounts in the individual transactions, and the transaction graph. Let me quickly explain what the transaction graph is. Note here that Barclays obtained these euros through JP Morgan. It shouldn't be able to be the case that an auditor can notice exactly who Barclays received the euros from and, in fact, how many transactions it used to receive the euros. So we can actually hide the values in a transaction pretty easily using a cryptographic primitive called Peterson commitments. Peterson commitments are binding and hiding commitments to a value, kind of like a hash. Everyone agrees ahead of time on a cyclic group with 2 generators, G and H, and then a bank chooses randomness R and creates a commitment to an amount V by producing G to the V times H to the R. Peterson commitments have a few very important properties. First of all, they're binding. It's very hard to open a commitment to a value other than the one that was originally committed to. Unlike a hash, multiple Peterson commitments can be homomorphically combined. If you multiply these commitments together, then the result is a commitment to the sum of the values. Peterson commitments are also very fast to create, combine, and verify. And perhaps surprisingly, we can achieve all of the auditing measurements I showed you before using just this basic primitive. Now, as we build up our example, we also want to be able to hide the participants in the ledger. This can be done using various techniques. I'm not going to go into that right now. Now, let's look at how an auditor can audit a bank that's using these commitments. The auditor will ask the bank, how many euros do you hold? And the bank will respond with an answer, 3 million. But the bank will also respond by opening up the commitments of the sum of these 2 transactions. The auditor can then go and compute the sum, the product of the commitments itself, and verify that this actually checks out. However, there are a couple of important problems with this right here. First of all, it reveals which transactions Barclays was in that received the euros. And more importantly, a malicious bank could just leave out transactions when responding to the auditor. So here, if Barclays were being malicious, when responding to the query, how many euros does it hold, it could say 1 million, and it could tell the auditor to just open up this one transaction. The auditor would have no idea that Barclays was also involved in other transactions that were relevant to the answer of this query. zkLedger addresses this with a very different kind of design for the ledger. In zkLedger, every transaction has an entry for every bank. So rows in zkLedger are transactions, and the columns are the transacting banks. So here we have a ledger which supports transactions between Goldman Sachs, JP Morgan, and Barclays. As we see here, depositor transactions are still public. But for private transactions, every bank will have a commitment in every transaction. The spending bank creates the transaction, and in its column, it commits to a negative amount. In the receiver's column, it commits to a positive amount. And in all other columns, so for the banks that are not involved in the transaction, it commits to 0. A very important thing to note here is that columns with commitments to 0 are completely indistinguishable from columns with commitments to non-zero values. So someone who's looking at this ledger can't actually tell which are the transacting banks. A key insight we had with zkLedger was to achieve completeness, the auditor can actually audit every transaction. So here, the auditor will ask Barclays, how many euros does it hold? Barclays will answer 3 million. And the auditor will ask Barclays to open up a commitment to every transaction in Barclays' column. So note here that Barclays doesn't get to pick and choose which transactions the auditor is going to look at. The auditor actually looks at them all. And because of this, the auditor is convinced that Barclays isn't leaving anything out. To see why this is the case, consider a malicious bank, which might want to lie to the auditor. The auditor would ask, how many euros do you hold? The bank would answer 1 million and would try to open up a commitment just to 1 million. However, the auditor would realize that this wasn't consistent with what was in the ledger and wouldn't accept this answer. So using hiding commitments in our table design, we're able to achieve the first two security goals, but we still need to show how we maintain financial invariance, and now we've added every bank to every transaction. So we want to be very careful here. We don't want to require interaction with every bank in order to produce a transaction. We achieve this using a set of non-interactive zero-knowledge proofs. These proofs are short binary strings. True statements have proofs, false statements only have proofs with very negligible probability, and the proofs themselves don't actually reveal why they're true. In zkLedger, we design the proofs very carefully to prove validity, but to also be completely non-interactive. We prove validity using the following set of NSDIs. There's one for consent, one to prove that a bank has assets, and another to prove that assets are conserved. But there's another set of proofs which allow a bank to produce a valid transaction without actually needing to interact with the other banks. If, for some reason, this bank produces an ill-formed transaction, everyone will be able to detect it, and they can reject the transaction from the ledger. And you can see our paper for more details on exactly how these proofs are constructed. Now I want to tell you a little bit about the performance of zkLedger. To start with, its implementation is as follows. It was written in Go. We use an elliptic curve as our underlying group for the commitments and the proofs. We use BTCEC, which is, uses the curve SecP256K1. And zkLedger itself is around 4,000 lines of code. Our evaluation tries to answer the following. How fast is auditing, given that the auditor has to compute over these commitments and verify all of these proofs? And how does zkLedger scale with the number of banks, since every transaction has to include an entry for every bank? We run these experiments on a set of 12 virtual machines. This first graph shows that simple auditing is actually very fast and is independent of the ledger size. So on the x-axis, we vary the size of the ledger. On the y-axis, we show time in milliseconds. And we see that for a set of 4 banks, where we're computing a measure of market concentration, it's only about 6 milliseconds. This is because Peterson commitments and the table design are actually very amenable to caching, and we use a technique called commitment caches. This means that when the auditor is auditing the banks, it only really has to do a couple of elliptic curve operations, which are very fast, and so most of this time is actually network round trip. More complex forms of auditing are linear in the size of the ledger. So we see here that for a ledger of 100,000 rows, the auditor, it takes about 3.5 seconds for the auditor to compute a more complex measurement. If we extrapolate this out in a ledger with 100 million rows, it would take about in a ledger with 100 million rows, it would take about an hour. It is possible to snapshot the ledger with commitment to certain state so that it doesn't need to grow forever, but zkLedger doesn't implement this. So auditing is pretty fast. Now let's take a look at how long it takes to actually process transactions. So in this graph, we vary the number of banks on the x-axis. And this is measuring the cost of one bank creating transactions, sending them to the ledger where they're committed, the ledger broadcasting them to all banks in the auditor, and everyone verifying all transactions. And what we see here is that in a system with 10 banks, it takes about 800 milliseconds to completely process a transaction. This is pretty reasonable. It means we can achieve our goal of tens of transactions per minute. To look into exactly where this cost is coming from, we can take a look at how much each entry in a transaction actually costs. So an entry is about 4.5 kilobytes. Creating an entry is 8 milliseconds and verifying it is 7 milliseconds. And this is basically all elliptic curve operations to produce the commitments and the various proofs. Remember, there is an entry per bank in each transaction, so multiply this times the numbers of bank to find out how long it takes to process a transaction. I'm actually quite optimistic about this because most of this work is very highly parallelizable, and we didn't actually make any effort whatsoever to optimize the underlying elliptic curve library, so I think that there's a lot of performance to be gained here. The design is also actually very modular, so if new proof systems come out that are faster, we can take advantage of them. To conclude, we have related work, and there are two classes of related work. The first type doesn't actually provide private auditing, though it provides privacy on distributed ledgers. The second category does some auditing for financial systems, but can't guarantee completeness. And then the two most closely related systems are Solidus. Our techniques might actually apply to Solidus, but they don't describe or implement auditing, and a system for accountable privacy and decentralized anonymous payments, which is really designed for policy enforcement, not necessarily auditing. So in conclusion, zkLedger provides practical privacy and complete auditing on transaction ledgers, and we do so with pretty reasonable performance. You can go to the following website to learn more. Thank you.
Yes, Neha. Any questions? Any questions? Well, I'll start with a question then. So you showed how zkLedger scales linearly in the number of banks. If you have, let's say, many banks that are participating or many organizations that now start to use your system, is there any hope to scale, let's say, sublinearly so that you avoid the cost of every transaction to require work for every single bank?
Yeah, we have some ideas on how to potentially scale zkLedger by sharding the ledger or sharding the sets of banks. We didn't go into detail on that in this work, so it's unclear exactly how that would work, but we have some ideas on how to potentially do it. For our use case, there were a limited number of banks, so it works out.
Cool, thanks. Any other questions? That's a question? Okay, great.
Hello, just a clarification question. So when you were talking about the transacting banks who are not participating doing a zero commit, how would somebody who's observing the ledger be able to not do like a frequency analysis or see that there are many more banks that are having the same like zero commit and then discerning the transacting banks from that?
Yeah, so actually you can't tell which ones are zero commits and which ones aren't. And commitments to zero are completely indistinguishable from a commitment to a different value. So, and this is achieved because each bank picks a different randomness every time they do a commitment.
Thank you.
Yeah.
Great. Any other question? Well, maybe the second speaker can start setting up, and I'll ask one last question during that time. So, in terms of the linear functions for auditing, do you think you can extend to more complex functions?
Yes, we are pretty excited about extending to more complex functions. There's some techniques in the paper that we use to sort of do recommitments. It's very slow, but I think that there's some things you can do, especially given that we're using Peterson commitments. We could think about using other types of commitments as well. So I'm optimistic about future work, but we didn't do it.
Cool, great work. I really enjoyed it. Let's thank Neha again.